What's going on? Sorry I'm late. Hey there, Herman. Looks like it might just be me and you.
Sorry, my internet's being weird.
That, that,
Oh
that,
yeah,
that
sure.
that's totally fine. I hope it doesn't help me do that too much, but but looks like it's me and you today. So if your internet goes down, it's just me. So I will do whatever I can to keep your internet up.
There we go.
How was your Halloween?
Yeah, pretty good. Just carved some pumpkins with my wife, and we just hung out. And that's it, really. Some friends.
Pumpkin carving.
Yeah.
I love Halloween so much. It is, in my opinion, like I don't know if I'm allowed to say things like this, but the best holiday. Way better than, well, I mean, I don't want to say it's way better than like any other holiday like Christmas or Thanksgiving or 4th of July, whatever. But Halloween, what I love about it is it's totally made up. I know you can make the argument that every holiday is made up, but Halloween feels really made up. Like, every October 31st for no reason. Why don't we just all like carve weird faces and pumpkins and eat a bunch of candy, give candy out to random kids that knock on the door, dress in costumes, watch spooky stuff? There's no reason for any of that, and all of it's fun. And I love the fact that we have a day dedicated to it.
Yeah, it's pretty cool. I enjoy the entire holiday as well.
Yeah, it's honestly inspiring. It shows us that really every day could be special if we all just decide to make it special. Like, why did people thousands of years ago like have a monopoly on creating holidays? It's a bunch of BS. Like, I mean, like even holidays we create, like 4th of July is pretty cool, I guess. But since then, like the modern holidays, I mean, I guess they're more somber, but I mean, for no one throws down for President's Day. You know what I mean? Like no one, like there should be a bunch of weird traditions that we can all get behind. But but anyway, welcome Herman, welcome Toru. But 2 cents on holidays. Sadly though, I'm not a holiday professor. I am actually I am a professor. I'm not a holiday instructor. I am a mathematics instructor. So let's talk about some math, specifically discrete math. Honestly, my favorite type of math that you guys haven't been able to tell. Yeah. And we are still talking about induction as we will all week long. Already with this. There we go. We are talking about weak induction right now. And by the end of class, hopefully we'll understand why we call it weak induction versus strong induction. And it's weak in the sense of the things you get to assume, not in the sense of its power to explain things or be awesome. If anything, it's stronger because of that. I guess it's kind of like, I don't know. Weak induction is more mentally strong, where strong induction is more physically strong. I don't know what you consider more strong. But anyway, the point is, let's just get going. So I've written down on a nice sheet of paper here what weak induction looks like. And remember the whole idea, we had dominoes, actually I had Jenga blocks last time, but the whole idea of like the dominoes chain reaction we were talking about is that if you have a claim that works for all integers greater than some number, right? In this case, I'm saying that for all integers greater than or equal to this random number a, P of n will be true, or P of n some property. Maybe it's saying that, n is greater than something. Maybe it's saying that n is divisible by something. Who knows? But it's just some claim about n. And the proof goes like this. You say proof by weak induction on n. You prove the base case is true. You prove that P of a is true. And then you show that for all n greater than or equal to a, if P of n is true, then P of n plus 1 is true. And if you've shown that, then what you've really shown is you've shown this, I have a Sharpie. You've shown a chain reaction, right? You've shown that P of 1 implies P of 2 implies P of 3. Actually, I guess this should be P of a implies P of a plus 1 implies P of a plus 2 implies P of a plus 3, on and on indefinitely. You've shown that, and you've shown that this is true by the base case. So the first part of your chain is true by the base case, but every part of that links via the inductive step. So you've proven that every integer greater than that is true, or it has this property. That's kind of cool. Apparently I have rhythm. Anyway, so this is a weak induction. So we're just gonna do a bunch of proofs and try to really cement this into your brains. I guess it's like if you see like people with wet cement put their hands in it. That's what I want to do right now. Your brain's a bunch of wet cement, and I'm gonna put my hands in it, and let's learn induction. So that was weird. Let's go with this claim right here for our first proof. So the first claim I want to prove goes like this. Any questions, by the way? About induction, not the weird things I say. Cool.
No, all good.
So the claim goes like this. N factorial is greater than 5n for all integers greater than or equal to 13. Greater than or equal to 13, which I write like that just to give us practice with writing things formally. And if you're watching at home, give this video a pause and try to do it yourself. This one's easy though. All this is saying is that we say n factorial is greater than 5n for all integers greater than or equal to 13. And notice this is kind of weird. And we had a problem in the homework like this that trips some people up. And it's weird because we have the for all part after what we're talking about here. But do not let that fool you. That's just a quirk of English, right? In English, the way the grammar works, you're kind of allowed to introduce things before or after you talk about them. You can say like, my amazing math instructor, Daniel, or you can say, Daniel, my amazing math instructor, right? You can go either way. That's fine. All depends on context, things like that. It's kind of like if you've taken any foreign language, right? Like the order of adjectives is really weird. Like we would say like, oh, this is a small red marker, this one specifically. But the French might say like, oh, this is a red marker small or something like that. I don't know. French was a long time ago for me. But the point is, different language systems have different orders in which they introduce things, and sometimes it's fluid. English is one of those. But mathematics, like precise logic, you can think of that as a language system, right? It's symbols that mean things, but it has a much more precise meaning for everything, and you can't really screw with it as much. And so one thing in logic, you always need to introduce the variables before you talk about them. So even though English makes sense to introduce in after you talk about it, in logic we need to say for all n in the set of integers greater than or equal to 13, n factorial is greater than 5n. And by the way, the set of integers greater than or equal to 13, you could write this as just the set of all integers such that x greater than or equal to 13. Yeah, so a little practice there, but this is what we're talking about here. And by the way, if you notice, we've never ever actually defined what a factorial is. So I'm going to do that right now in front of everybody. So any questions on this, by the way? This is a give and take. I don't want to keep giving and giving and giving without you even having a chance to take. Okay, so factorial, and I'm gonna underline fact. This is a fact about factorials. And this is the definition. So for all n in the natural number, so integers greater than or equal to 1, n factorial is defined to equal the product from I equals 1 to n of I. And a lot of you guys have seen it before, but this is it using the notation of product that we talked about a few times ago. And remember, what this product means is this means this means you do the sum, or no, sorry, is the repeated product of this term right here as I ranges from 1 to n. So when I equals 1, I is just 1. When I equals 2, I is 2. When I is 3, I is 3. We go all the way up to n. So this is that, all the way out to n. So this is what n factorial means. It's 1 times 2 times 3 times 4 all the way out to n. So for example, let's go pink or red. For example, 1 factorial is just the product of everything from 1 to 1, which is just 1. 2 factorial is the product of everything from 1 to 2, which is 2. 3 factorial is the product of everything from 1 to 2 to 3. 1 times 2 is 2 times 3 is 6. 4 factorial is the product of everything out to 4, which is 1 times 2 times 3, which you found is 6, times 4 is 24. 5 factorial is 1 times 2 times 3 times 4 times 5, which is 1 times 2 times 3 times 4, which above we found to be 24, times 5 is 120. And it goes on like this. That's a factorial. And fun fact, hope this makes sense. I'm going kind of quick because I think most of us have seen this before. Stop me if you haven't. Stop me if you heard this one or haven't heard this one. So yeah, so that's a factorial. Fun fact about factorials, and you guys will learn this next semester if you take combinatorial, which I highly recommend, really fun class. The fun fact is that n factorial represents the number of ways to pick in different items out of a hat. So if you had a nice, do I have a hat with me? I don't have a hat. But if you had, I have some hats up there, whatever. If you had a nice hat, right, with a bunch of crap in it, with a bunch of things in it, with in items in it, let's just say n was 3 with 3 items in it, there'd be 3 ways to pull things out of that hat. Like if you had ABC, you could pull out ABC, you could pull out ACB, you could pull out BCA, you could pull out BAC, and you could pull out CBA and CAB or whatever. I think I actually nailed that. The point is there's 6 different ways you can pull those things out of the hat. That's what n-factorial represents. Also fun, or that's not what it represents, it just happens to be what it is. Also fun fact, 5 to the n represents the different number of ways to pick in things out of a hat if there are only 5 things that are replaced after every pick. So in factorial, that's the scenario where there's n different things in the hat and you're just picking them out until you're out of things in the hat. 5, and the number of ways you can do that. 5 to the n represents the number of ways you can pick out of the hat in the scenario where there's basically, imagine like you just pick in things and you go, but after every time you just replace it. So if I have like 1, 2, 3, 4, 5, let's get rid of these 2. If I have 5 markers here, right? This is the number of ways where I can pick a marker out. Oh, I pick green, you put it back. Next pick is orange, I put it back. Next pick is pink, I put it back. Next pick is orange again, I put it back. The point is, in that scenario, we always put it back, but it's just the number of ways you can do that. That's going to be 5 to the n. So really what this question is saying is that for all n greater than or equal to 13, it seems that the number of ways you can pick in things out of a hat and not replace them is bigger than the number of ways that you can pick in things out of a hat. There's only 5 things and you always replace them. This is combinatorics. You don't have to know this. I just wanted to show you this to show you that this kind of stuff actually has some real world applications. We were talking about, especially in computer science, we were talking about like the number of different ways things to be sorted and things like that. Combinatorics comes up a lot, and probabilities come up a lot and things like that. And induction can help prove things about it. You thought we were just screwing around this whole time. I'm actually teaching you knowledge. So, between the fun, we actually learn useful things. So let's get out our claim here. And remember how we're going to prove this. We're going to try to prove this by proving the base case and then proving the inductive step. That P of n implies P of n plus 1 for all n bigger than or equal to the base case. The proof goes like this. Proof. It would say proof by weak mathematical induction on n. So here we have the base case. In the base case, what we're trying to do is we want to show that P of 13 is true, and this is where we make in factorial greater than 5n, we make this equal to P of n. So if that's like your predicate, you're saying P of n is true if n factorial is greater than 5n. We want to show P of 13 is true, i.e. 13 factorial is greater than 5n. So let's just do it. So we're going to say let n equal to 13. Then note that n factorial equals 13 factorial, which if I get out my calculator, or let's see if Siri's got this. Siri, what's 13 factorial?
13 factorial is 6,227,020,800.
Look at that. Thank you very much, Siri. So according to Siri, 13 factorial is 6,227,020,800. So that's 13 factorial. The number of ways you can pick 13 things out of a hat, you'd almost get all of Jeff Bezos. You get like a small percentage of Jeff Bezos' net worth. So that's n factorial. Further, the question is 5 to the n, which equals 5 to the 13. What's that, Siri? Siri, what's 5 raised to the 13th power?
5 raised to the 13th power is 1,220,700,8,125.
So according to Siri, that's 1,220,703,125. The point being, just checking 5 to the 13 and 13 factorial, we see 13 factorial is in fact bigger than 5 to the 13. Thus, n factorial, which equals 13 factorial, is in fact bigger than 5 to the 13, which equals 5 to the n. Hence, the base case holds. So the base case is much more computational. It just we have to show this one thing is true, just do it. All right. Any questions on that? Good. So that brings us to the inductive step. And here, remember, we want to show that P that for all n greater than or equal to 13, as to connect to the base case, P of n is greater, or sorry, P of n implies P of n plus 1. So in our particular example, we want to show that for all n greater than or equal to 13, n factorial greater than or equal to 5 to the n, n factorial greater than or equal to 5 to the n, or maybe I'll say if n factorial greater than or equal to 5 to the n, then n plus 1 factorial is greater than or equal to 5 to the n plus 1. So that's what we're trying to show. And I just remembered that I meant to give you guys a lemma to do this, to help do this. We can do it without it, but well. And the lemma says, for all real numbers, or I'll say for all positive real numbers, A is greater than B and X greater than Y, AX is greater than BY. Which I think makes a lot of sense, right? We're saying if A is bigger than B and X is bigger than Y, then certainly A times X, right? The product of the two bigger things is bigger than B times Y, the product of the two smaller things. But we haven't proven it yet. So theoretically, if I didn't tell you this, you need to prove it. But I'm telling you this is a fact, so you don't need to prove it. Maybe I'll prove it later if we have time. Probably not. So anyway, let's just get started. So we want to show this, right? This is a for all statement. So we have a mini proof here inside of our inductive step, which is a for all statement. The way to prove a for all statement, you could use method of exhaustion. We can't do that because we have an infinite set here. So instead, let's use a direct proof. So let's go ahead and say, let n be any arbitrary / particular integer such that n is greater than or equal to 13. So we have the domain, right? And now we want to assume the hypothesis. We want to assume the hypothesis and show the conclusion. We want to say that in the assumption that n factorial is greater than 5n, we can show n plus 1 factorial is greater than 5n plus 1. So assume n factorial is greater than 5n. All right. Now, how do you guys think we can get from this fact to proving this?
You can turn n plus 1 factorial to n factorial times n plus 1.
You're saying n plus 1 factorial is n plus 1, perfect, yeah, times n factorial, exactly.
And then you could turn 5 to the n plus 1 to 5 times 5 to the n. And then you can use the lemma. I don't know how you would prove that n plus 1 is bigger than 5, though.
I'm glad that
Oh, wait. It's bigger than 13.
it's bigger than 13.
Yeah,
So it's
it has
clearly
to
bigger than 5.
Yeah.
Yeah, Tor, this is a fantastic idea. Tor recognizes that, hey, we can get from n to n plus 1 factorial just by multiplying n factorial by n plus 1. Because that's what it kind of means, right? N factorial is the multiple of everything from 1 to n. But if you multiply an n plus 1 on top of that, well, this whole product is the multiplication of everything from 1 to n plus 1, which is n plus 1 factorial. And then he also recognizes that 5 to the n is 5 multiplied by itself n times. We multiply another 5 on top of that, that's 5 multiplied by itself n plus 1 times. So if you know n factorial is bigger than 5n, which you're saying it is by assumption, and n plus 1 is greater than 5, which it must be because n is greater than or equal to 13, meaning n plus 1 in particular is bigger than or equal to 13, which is bigger than 5. Well, by our lemma, right, if you multiply the two bigger things, it'll be bigger than if you multiply the two smaller things. So n plus 1 times n factorial should be bigger than 5 times 5 to the n. But like we just argued, this is just n plus 1 factorial on this side, and this is just 5 to the n plus 1 on this side. Very good, Toro. Very, very good. And this time I'm not giving Liam credit. That's something you did. That's all you, Toro.
That it was all me.
So that's the idea. So let's note a couple things. Let's say note, since n is greater than or equal to 13, n plus 1 is greater than or equal to 13 plus 1, which equals 14. By adding 1 to both sides. Normally we do this in kind of like the center. We'd say like, oh, n plus 1 is greater than 13 plus 1, but since it's just one line, you can do it like this. Yeah, so further, n plus 1 greater than or equal to 14 is greater than 5. Thus, by transitivity, n plus 1 is greater than 5. That just says that because n plus 1 is bigger than or equal to 14, 14 is bigger than 5, n plus 1 is bigger than 5. Which makes sense, right? Hence, by our lemma, because n factorial is greater than 5 to the n, and n plus 1 is greater than 5, then n plus 1 times n factorial is greater than 5 times 5 factorial. So that's the big idea right there using the lemma. Then we can use Torio's great observation to show note that n plus 1 times n factorial greater than 5 times 5 factorial by given by above. That implies that n factorial is greater than 5 times 5 factorial, or sorry, n plus 1 factorial by definition of factorial. And that implies n plus 1 factorial. All right, this would be, sorry, oh my gosh. This is 5 times 5 to the n. What am I doing? I'm just trying to transcribe that line there and I messed it up twice. So the n plus 1 times n factorial greater than 5 times 5 to the n, meaning n plus 1 factorial, we said that that's what this equals, greater than 5 times 5 to the n. And then 5 times 5 to the n, we said is 5 to the n plus 1 by definition of exponentiation. Thus, assuming n factorial is greater than or equal to 5 to the n, we have shown n plus 1 factorial is greater than 5 to the n plus 1. So what this means is that if at any point, if at any n factorial gets bigger than 5 to the n, well, it's guaranteed n plus 1 factorial is bigger than 5 to the n plus 1. Meaning it's guaranteed that 5 to the n plus 2 factorial is bigger than 5 to the n plus 2. It's guaranteed that that or like n plus 2 factorial is greater than 5 to the n plus 2. N plus 3 factorial is greater than 5 to the n plus 3. Then you have that chain reaction. It just keeps going forever. Once you show it happens once, it'll happen for all n bigger than equal to that. And that's where the base case comes in because we showed it once. We showed it works for 13, so it must work for everything bigger than equal to 13. And so here's the part, I'll put the conclusion down here in blue. This is normally where you have conclusion. N factorial greater than 5 to the n for all integer n greater than or equal to 13. Any questions?
Why 13?
That's a good question. Because I have actually a table that I have on my graphing calculator app here. Well, in the beginning, clearly 5 to the n is going to be bigger than n factorial because, like, for example, if you look at 3 factorial, that's 3 times 2 times 1, where 5 to the 3 is 5 times 5. So, so every factor there in 3 factorial, 1, 2, and 3 is less than 5. And so clearly 3 factorial is going to be less than 5 to the 3. Same thing with 4 factorial. That's 1 times 2 times 3 times 4. And 5 to the 4 is 5 times 5 times 5 times 5. Again, every factor in the 5 case is bigger. Once you get to 5 factorial, you get to the first one where it's kind of like you have one factor that's equal. You have 1 times 2 times 3 times 4 times 5. Whereas 5 factorial, you have 5 times 5 times 5 times 5 times 5. So almost all the factors are bigger, but not quite. The point is, if you play that logic out, it turns out you have to get to 13, I think. Actually, let's see if 12 actually works. No, 12 doesn't work. So you have to get to 13 to find the first one where finally n factorial can eke past 5 to the n. And you think it should eventually, because once you get past a certain point, like 5 is just multiplying 5 times 5 times 5 times 5 times 5. Once you get 13 factorial, you do 1 times 3 times 4 times 5, smaller than 5, but then times 6, times 7, times 8, times 9, times 10, times 11, times 7, times 13, right? All bigger than 5. So there's like a balance there that eventually gets overcome between 12 and 13. Make sense, kind of? Yeah, and that's actually the weird thing about induction. And that is, and I mentioned this in in the page I put up yesterday, but that is that induction is beautiful because it's kind of like contradiction in the sense that contradiction and induction both allow you to prove things that feel almost impossible to prove. You don't have enough information, but you can put that information together in a very particular way to actually prove something really incredible. But contradiction and induction both have the weakness that they don't give you much understanding as to why something's true. Like induction is a very computational process almost. You show the base case is true, then you show P of n implies P of n plus 1, and then the answer just falls out. But if anyone asks you why is that true, like if anyone asks you, hey, why is the summation of n equals 1 or I equals 1 to n of I, why does that equal n times n plus 1 over 2? You proved it by induction, but you don't really get to the crux of why this is true. You have to go to more of Gauss's whole situation to figure out why this is true. So it's kind of interesting how proving something true can sometimes be separated from the core concept of why it's true. But anyway, we're going to do that. I think this is actually the opposite. I think this induction proof actually helps you actually really understand things. And this is something that we've talked about before. And I might get an eye roll. Good thing all your cameras are turned off. And that is prove that every natural number is even or odd. Yeah, remember this guy? Remember this really complicated, stupid proof that we use contradiction in a weird way to prove this? Don't leave the screens. It's all right. It's all right. It's a safe place. This is actually being a lot easier with induction. I wanted to show you that you could do it with contrapositive, but induction is the real way to do this. And actually doing it with contradiction kind of shows you that, hey, the proof technique you use really matters, right? You can work smart, not hard. So here, here's the idea. The formal claim of this would be that for all n and the natural numbers, n is even, or I'll say n even, or n odd. And it should be noted that the natural numbers are simply all the integers that are bigger than or equal to 1. So this totally fits our form of trying to prove something for all integers greater than or equal to some a. The a here just happens to be 1. Let's just get into it and we'll talk about things. So the beginning of a induction proof always works the same. You don't have to think that hard. You say proof by weak mathematical induction. Proof by weak mathematical induction. And then from there you say, on n, that's the variable we're kind of going through here, like as n, we're ranging in. And their base case. And remember here in our base case, what we want to do is we want to show that P of 1 is true. Because we're trying to show it's true for everything bigger than or equal to 1. So you want to start at the bottom, show P of 1 is true. I.e., in this case, we want to show that 1 is even or odd. Real simple. I'll say let n equals 1. Note 1 equals 2 times 0 plus 1. Since 0 is an integer, 1 is odd by definition. So 1 is even or odd. It's odd in this case. Thus, the base case holds. Real simple. 3 lines to prove that 1 is odd, but we didn't. Here's the inductive step. Remember, base case is computational. Inductive step is the more clever, interesting part. So the inductive step we want to show for all n bigger than or equal to 1, P of n implies P of n plus 1. In our particular case, we're trying to show that for all n greater than or equal to 1, if n is even or odd, then n plus 1 will be even or odd. So why is that true? Let's think about that, right? If n is even or odd, why is n plus 1 even or odd? So what do you think we should do with n, first of all, here? If we know n is even or odd, what's kind of a good proof technique to simplify things some?
Either 2k or 2k plus 1 maybe.
Totally, we're gonna do that. I say even broader proof technique. Let's just divide into cases, right? Let's look at each case
Okay.
and see what happens. And so it sounds simple. I mean, this is problem solving 101 right here. This is a really important problem solving idea. It's the idea of you have a problem that's too hard to solve, break it into smaller problems and try to solve each of those. So a case of, and by the way, that's a recursive thing. Each of those smaller problems is still too hard, break the smaller problems into smaller problems. So case 1, if we have n even, well then n's gonna equal 2k, right? So what do we know about n plus 1?
It's odd.
Yeah, then n plus 1 is gonna equal 2k plus 1, which is odd. Case 2, n is odd. Like Tor said, we can write that as 2, n equals 2k plus 1. What do we know about n plus 1 then?
It's 2k plus 2, and then you could take out a 2.
Exactly. And so since k plus 1 is an integer, because k is an integer, 1 is an integer, integers are closed under addition, that means this is even. So this is Domino's ass finest. That's absolute finest. Right here, we started with n even, right? And we started with n even or odd. If n's even, well, hey, if you add 1 to that, you get an odd number. If n's odd, you add 1 to that, you get an even number. That's the chain reaction. 1's odd, so 2's even, meaning 3's odd, so 4's even, 5's odd, 6 is even. The point is, every single integer there is hit, and every one of them has to be even or odd, none are skipped. That's so much simpler than whatever we were trying to do before, with like weird contradiction of like, let's take all the even numbers less than this and figure out what happens. So much simpler. And it makes sense. And the reason this kind of makes sense is because inherently the natural numbers are inductive. They're actually defined inductively as a thing you don't even know, but they are. So that kind of makes sense though, because like each even number or each natural number is just 1 plus the natural number before it. So you start at 0, add 1 to get to 1, add 1 to get to 2, add 2 to get to 3. It's a recursive inductive definition. So it kind of makes sense that that an inductive proof might work on it. So let's get to proving it. So that's the idea. Let's make it formal. So remember, trying to prove this claim for all n greater than or equal to 1, if n is even or odd, then n plus 1 will be even or odd. This is a universal conditional statement. So the way you prove that is you first just let n be something in the domain, something arbitrary particular, assume the hypothesis, you need to show the conclusion. So let's say let n be any arbitrary / particular integer such that n is greater than or equal to 1. Assume n is even or n is odd. I could break into cases. Case 1. I didn't like the look of that. Case 1, there we go, much better. N is even. Then, by definition, n equals 2k for some integer k. For some integer k. Thus, n plus 1 equals 2k plus 1 by adding 1 to both sides. Since k is in Z, n plus 1, which equals 2k plus 1, is odd by definition. So in case when we show that if n is even, then n plus 1 will be odd. It's got to be. And I'm actually going to erase this to save some room. I'll keep the important bits. Be cool? So if n is even, then n plus 1 will eventually get to n plus 1 is odd. Case 2. N is odd. If n is odd, then n equals equals 2k plus 1. And actually, I'll say 2t plus 1 for some t and z. The reason I'm doing that is because I used k above. Technically, it's okay. It's like in computer science, if you have like two different methods, you can use the same local variable twice. That's fine. Very similar concept here, but just to avoid confusion, I'll make it different. It is odd that n equals 2t plus 1 for some t and z. Then n plus 1 equals 2t plus 1 plus 1 by adding 1 to both sides, and that equals 2t plus 2 by associativity, and that equals 2 times t plus 1 by factoring out 2. Then, since t and 1 are in z, and z is closed under addition and multiplication, or actually z is closed under addition, t plus 1's in z. Thus, n plus 1, which equals 2 times t plus 1, is even by definition. So starting with n is odd. The n is going to be 2t plus 1. So you add 1, you get 2t plus 2. Factor out the 2, you get 2 times t plus 1. So n plus 1 is even. Starting with n even, you get n odd. Starting with n odd, you get n even. And again, I'm going to erase this to make room. It's okay. Perfect. So starting with n odd, we do our proof. This is like in computer science when you take a method and you like collapse it so you don't have to look at it. Then n plus 1 is even. Thus, in either case, n plus 1 is even or odd. So you start with n even or odd, right? If you ever get to a point where n's even or odd, then the next number after that will also be even or odd. Therefore, the next number after that will also be even or odd. The next number after that will also be even or odd. That starts your chain reaction where everything after that's even or odd. And luckily, we have a base case of n equals 1, and that's even or odd. It's odd, so it works out. So conclusion, therefore, for every natural number n is even or odd. Oh. Square, we're done. Oh, nice. Beautiful. This is the exact power of induction right here, right? We had a proof that before we said, wait, this is really simple. Everything's even or odd, but it was really, really hard to prove. Like, how would you actually show that there can't be a single number out there that is skipped by the evens and odds, just somehow is missed? And this is how you show it. You show that every integer is 1 plus the integer before it, and that necessitates that it's even or odd. It just keeps going like that. It's even or odd, even or odd, even or odd, even or odd, even or odd. Any questions? All right, so I'll do one more example and call it a day. Now, note, by the way, that we could also obviously show that 0 is even, and then we could kind of do like the reverse of this argument on the negative natural, or like the negative numbers, negative integers, or you could even just say that, oh, every negative number that's -1 times a natural number, and that's going to go the same direction as that number is, right? Like if like 2's even, -2's even, 3's odd, -3's odd. So you can kind of prove it that way. The point is the same idea holds for all integers. I just did it for natural numbers to keep things a little cleaner because we're just learning. All right, last claim. This is going to be weird. You're finally we get to it. It's like a family trees. Specifically, let's look at Merida's family tree. Do you guys know who Merida is? Turu clicked the unmute button, which the equivalent of going,
No clue.
no one knows who Merida is? No one knows who this strong young role model is from the Pixar movie Brave? Merida?
Of course.
Yeah, obviously. Yeah. So this is the Merida I'm referring to. I don't know what this is about. Let's play some Mexico. Look at that. Anyway, we're talking about the fictional Scottish lady, Merida. So, let's look at her family tree. Starting with her. So I'm going to call the generation that includes her G0. Like that's the OGs. I guess you could also put it OG, but I'm going to say OG0. And then the next generation, I'm going to call G1. So let's say, she comes down and she has 3 kids. Let's call the next generation G2, all the kids they have. So maybe it looks something like this. Let's call the next generation G3. Maybe it looks something like this. Like that. That's all wonky. I think you see my point. So this is G0, this is G1, this is G2, this is G3. So there's a few things to note here. So GN represents the nth generation after Merida. I feel like iPhones, these people. They're different generations. We're going to say, let G be all equal the set. So G with no subscript equal the set of all descendants of Merida and Merida herself. Which, once we learn set theory, we can write as GU union G1, union G2, union G3. Keep going and going and going. She could have more generations than this. The union just means combine these sets. So it's just combine generation 0 with 1, with 2, with 3, all the way out. These are all the possible descendants of Merida, including Merida herself. So a couple things to note. Note in this setup, right, for all X and G, if X is in generation Gn, then X's children are in the next generation, Gn plus 1. The same thing works in reverse. For all X in G, I'll say except Merida. If X is in G and then X's parents are in Gn plus 1. All right, like if you're this guy right here in G2, well, your parents is in G1. All right, actually, I'll say X has a parent. Has a parent Gn plus 1. Because it probably has one parent from out of the family, I would hope, that marries in. But the parent in the family is from Gn minus, or look at me, Gn minus 1. The above generation. Does that make sense? Good. So we have 2 facts about Merida's family tree we're going to use. We have fact A, and that is Merida is redheaded. Very true. We have fact B, and this one is only true for Merida's family tree, and that is for all X and G, if X has a redheaded parent, then X will be redheaded. This is in the fictional universe where it's a very strong strain of redhead that's actually become a dominant G. These are the 2 facts. And here's the claim you want to show. The claim you want to show is for all X and G, X is redheaded. And this should make sense. This has induction written all over it, right? We know that Merida starts as redheaded. And then we know that for every X in this family tree, if the parent's redheaded, then they'll be redheaded. So if you look at G1, well, they all have a parent of Merida. And so that means that they should all be redheaded because Merida's redheaded. Then you go to G2, and they all have a parent in G1, and everyone in G1 is redheaded. So that means they'll all be redheaded. G3, G4, G5, it goes like this. This is dominoes, just a little more complicated because we're talking about sets versus numbers. So it's 3:30 so later. I totally get it, but I'm going to prove this real quick, and this is going to be on the internet for you to see. But anyway, so let's just prove this by induction real quick. So let's say proof. Proof by induction. Weak induction on N. So the base case. So here in the base case, we want to show that in a certain sense, P of 0 is true. Actually, wait, this is interesting. Because here it's not, from the claim, it's not inherently obvious what the induction is going to be on. Like most of the time we had like, it was just N and the induction was on N. But here I say X is redheaded. There's no mention of really numbers increasing at all. So here's what I'll note. I'll say, this is equivalent to saying for all N in x and z such that x is greater than or equal to 0. Starting at 0 for all in that. And for all x in Gn, x is redheaded. The idea being that this family tree is made up of all these distinct generations. So if you can prove that every generation is made up of entirely redheads, then you can show that everything in this family tree, everyone in this family tree will be redheaded. So that's our idea. So rather than trying to prove it for everyone at once, let's prove it for each generation at a time using induction. So saying that it works for everyone in the family tree is the same thing as saying that for each generation, they're all redheaded. Does that make sense? This is a very interesting idea, the idea of breaking your big set up, all x and g, into multiple little sets that might depend on each other. Stop me, this doesn't make sense. Does it make sense?
Yes.
Perfect. So our base case then, we want to show that our base case is going to start with G0 then, if their n is ranging through the generations. We want to show that every x in G0 is redheaded. So here's what I say. I'll say let n equal 0, starting at generation 0. Then there's only one person in Gn, which equals G0, and that is Merida herself. Now, by fact A, Merida is redheaded. Thus, every x in Gn, which equals G0, is redheaded. Really simple. Just this G0 contains one element, Merida. She's redheaded. That's everything that's redheaded. Done. That's for the inductive step. Now here in the inductive step, we want to show that for all n greater than or equal to 0, right? 0 because that was the base case. We want to show this connects. For all n greater than or equal to 0, P of n implies P of n plus 1. In this case, what we're saying is that if every x in Gn is redheaded, then every x in Gn plus 1 will be redheaded. And maybe I don't want to use x twice here. I'll say y. For every y in Gn, that's if every y in Gn is redheaded, then every x in Gn plus 1 will be redheaded. If we can show that, that's our link. That is our chain reaction, right? That means that if at any point every one of generation is redheaded, then the next generation will be redheaded, the next generation will be redheaded, on and on and on and on. So here is where I move this up and get out a sheet of paper with a Sharpie and finish it like that. So here's the idea. Two sheets of paper because it bleeds through. So here's the idea. How can we prove this? Let's go ahead and let n be an integer such that n is greater than or equal to 0. Can you guys see this Sharpie okay?
Yeah.
Perfect. So let me integer such that n is greater than or equal to 0. So that's good because we want to show this for all n greater than or equal to 0. Now we have this if then statement here. They're trying to prove for all these n. And we're trying to prove, so it's still hypothesis and then conclude the conclusion. So then assume that for all y and gn, y is redheaded. So that this is weird, but the hypothesis here is actually a for all statement itself. But it's fine. It's just saying that for all y and gn, y is redheaded. That is the hypothesis. Now we want to show that, so now we want to show that every x and gn plus 1 is also redheaded. So how do we do that? Well, we're trying to prove a for all statement. We're trying to prove this works for every x. So let's just let x be any arbitrary element there. Let x be any arbitrary element in gn plus 1. Maybe I should say person instead of element. You see what I'm saying? Element of complement. That means you're in the fabric of math. So x be any arbitrary element in gn plus 1. And what can we do from there? If x is in generation n plus 1, how can we figure out that it's redheaded? Well, we're probably going to use this fact, right? This fact says that if x has a redheaded parent, then x will be redheaded. So all I have to do to prove that x is redheaded is prove that it has a redheaded parent. And if x is in gn plus 1, then generation n plus 1, what do we know about its parent?
The parent is in g of n minus 1.
Well, not g of n minus 1, because that'd be 2 generations up.
Just g of n.
It's g of n, right?
Oh, right.
Yeah, yeah. So x be any arbitrary element n. Then note, as a parent, let's call it y and g of n. By our assumption, since y is in g of n, y is redheaded, right? The whole thing was we're trying to prove that if we assume that every person in generation n is redheaded, then we can show every person in generation n plus 1 is redheaded. So since y is in generation n, we've assumed it's redheaded. Thus, by fact B, since x has a red-headed parent, mainly y, then x is red-headed. So since x is an arbitrary particular element in g of n plus 1, we showed x is red-headed, that means thus every x in gn plus 1 is redheaded, which is exactly what we're trying to prove. We're trying to prove that if every y in gn is redheaded, then every x in gn plus 1 will be redheaded. So we showed that if at any point a generation is entirely redheaded, the next generation must also be entirely redheaded. And the next generation must also be entirely redheaded. The next. This is the chain reaction. This is the induction. We just need one base case to ground it in reality, and that is Merida. Conclusion. for all n greater than or equal to 0, every x in g of n is redheaded. Thus, every one in G is red. Oh, you guys can see that. Any questions? So this is kind of easier, kind of harder, right? It's kind of like a family tree. Obviously, this is true. If you assume that if X is a redheaded parent, they're redheaded, then clearly since Meredith started as redheaded, everyone in this family tree will down the line be redhead, go on like that. But it's a little tricky to prove because we had a bunch of universal statements to deal with, but don't let that fool you, right? Just kind of, this is kind of like the grind, right? In the sense that you start off in the inductive stuff, you want to prove that for all n greater than or equal to 0, you have this if then statement's true. Well, that means it's a universal conditional. We know how to prove universal conditionals. Let n be any arbitrary element in that set. Assume the hypothesis and show the conclusion. It just so happens the hypothesis and the conclusion are both universal statements themselves, but that's okay. Any questions? Well, I am way over time. So I think maybe next week after the test, I will reward you guys with only 2 lectures or something like that to make up for my I don't know what the words are being for my incapability to understand time and how long things take. But anyway, hope this makes sense. With this knowledge, you should be able to prove 2 of the 3 things on the homework due Saturday, and then the next one, and then Thursday, we'd have to go to prove the last one. So anyway, yeah. No one has any questions. Have a great day. Sorry I went over. I'll see you guys when I see you.
Thank you.
Yeah, thank you.
You're welcome. Thank you. I hope this stuff is interesting.